Okay, so let's start. Good afternoon, everyone. I welcome you all again for today's live session. So for today's session, the agenda is we are going to see the basics of signal, that is specifically an electrical signal that we transmit through a transmission media. So a data, it can be an analog data or it can be a digital data. So the term analog data, it refers to the information that has the continuous value, whereas the digital data, it refers to the information that has the discrete values. So for example, an analog clock that has three hands, specifically one represents hour, one represents minute, and the third represents the second. So these hands, they gives us the information in the continuous form. The movement of the hands, they are basically continuous. On the other hand, if we take an example of digital clock that reports the hour and the minutes, and specific time like 12:20 p.m. to 12:21 p.m. Okay, so the analog data, such as the sound which is made by the human voice, which takes on the continuous value. So when someone speaks, an analog wave is created in the air, and this can be captured by the microphone, and it get converted into an analog signal, or later on it may get sampled, and it is then converted into a digital signal. So the digital data, as we mentioned, it takes the discrete value. So for example, the data that we store in the computer's memory, that is in the form of 0 and 1. So that is a digital data. So digital data is represented by using these two digits 0 and 1. So they can be converted to a digital signal, or they can be modulated into an analog signal for transmission across the medium. Okay, so the data, it can be analog or it can be digital. Then we'll see the analog and digital signal. Okay, as I have just mentioned here, what is the analog data and what is the digital data. Now it's time to see what is the analog signal and the digital signal. So signals, it can be analog or it can be digital. So like the data they present, the signal can either be analog or digital. An analog signal, it has infinite levels of intensity over a period of time. As the wave moves from some value A to some value B, it passes through, and it includes the infinite number of values along its path. So for example, if I pass the some signal, or you can say that if I pass a wave from some value A to some value B, for example, from 1 meter to 2 meters. So during this path, the signal takes, or the you can say that the wave, it takes the infinite number of values. So a digital signal, on the other hand, it can have only a limited number of defined values. Although each value can be any number, so it is often as simple as 0 and 1. The simplest way to show the signal is by plotting them on a pair of perpendicular axes, where the vertical axis represents the value or the strength of a signal, and the horizontal axis it represents the time. So here, this first figure, it shows the analog signal, and the second figure, it shows the digital signal. Okay, so this is basically an analog signal, whereas this is a digital signal. So why this is a analog signal? The curve representing the analog signal, which is where the signal passes through a infinite number of values. So you can see that the values start from here 1, 2, 3, dot 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 dot. So every dot on this curved line, it represents some value, and that's the reason the signal has the continuous values. Okay. Now the vertical lines of the, you can see that in the digital signal, however, it demonstrates the sudden jump that the signal makes from one value to another value. So here you can see that the signal has made some sudden jump from one value, that is from value, say that at this point it is 0 and at this point it is 1. Okay, so there is a sudden change in the value of the signal from 0 to 1 or from 0 to some x value. Okay, and that is basically the important difference between the analog signal and the digital signal. So what is analog signal? So analog signal is the signal which contains the infinite number of values, right? Whereas the digital signal, it has the discrete values. So now we'll go to the next slide. So in data communication, we commonly use the periodic analog signal and the non-periodic digital signal. So both analog and the digital signal, they can take one of the two forms. It may be periodic signal or non-periodic signal. So non-periodic signal sometimes referred as a periodic signal. What is a periodic signal? A periodic signal, it completes a pattern within a measurable time frame, and that time frame is called as the period, and repeats that pattern over the subsequent identical periods. So the completion of one full pattern is called as cycle, or it is also referred as period. A non-periodic signal, it changes without exhibiting a pattern or a cycle that repeats over a time, and that we are going to learn in an upcoming slide. Hence, both analog and digital signal, they can be periodic or non-periodic. But specifically, as mentioned here in a data communication, the periodic analog signals are preferred and the non-periodic digital signals are preferred over the non-periodic analog signal and periodic digital signals, right? Why we prefer the periodic analog signals and the non-periodic analog signal? So the reason is that as they needs the less bandwidth during the transmission of the data from the medium, may it be a physical medium or air medium. So we want to send data which consumes a less bandwidth, which consumes a less space of your transmission medium. And this is one of the important reasons why we choose the periodic analog signals and the non-periodic digital signals. So let's see what is periodic and non-periodic digital signal. So a periodic analog signal, it can be further classified as a simple periodic signal or a composite periodic signal. A simple periodic analog signal is, for example, a sine wave, which cannot be further decomposed into a simple signal or further multiple signals. On the other hand, on the counterpart, the composite periodic analog signal is composed of multiple sine waves. Okay, so now it's time to see what is the sine wave, what are the different parameters used to represent the sine wave, how do I calculate the speed of the data during the transmission medium. For example, if I send some data of 1 MB on a transmission medium which has the 1 kilohertz or a 1 megahertz bandwidth. Okay, so that's we are going to see. Then how can we represent the sine wave using the time and the frequency domain? Then we are seeing that, then we will see that how do we create a composite periodic analog signal which is composed of multiple sine waves and so on, and then some of the basics of bandwidth. So basically we are going to deal with the bandwidth as well. So let us start. So my today's agenda is to at least finish the time and frequency domain, the representation of signal using time and frequency domain. Well, this figure, it shows a sine wave. So what is sine wave? The sine wave is most fundamental form of periodic analog signal. So if I say what is sine wave is a periodic analog signal. So when we visualize it as a simple oscillating curve, then it changes over the course of cycle, where the cycle of these waves, these sine waves, they are very consistent, they are continuous, and they are rolling flow. Okay, so cycles are consistent. So you can see it here. This is one cycle, this is another cycle, and this is third cycle. The wave is rolling over the time, as well as the wave is very smooth. Okay, so these are some, we can say that the characteristics that we have found out for a good sine wave. Okay, the good sine wave, which is smooth, which has a continuous values, and which is rolling over the time, so which is flowing over the time. So now each cycle consists of a single arc. Let me take a erase so that it is here. So each cycle in this sine wave, it consists of single arc above the time axis and followed by a single arc below the time axis. Okay, so that is given here. So a sine wave can be represented by three parameters: the peak amplitude, the frequency, and the phase. So these three parameters are used to represent a sine wave. Remember, I will repeat it. The three parameters are used to represent a sine wave, mainly amplitude, frequency, and the phase of your sine wave. So that represents the sine wave. So let us discuss these three parameters in some more detail, so that we get a better representation of a sine wave when we are dealing with the sine wave as a part of transmitting media through the transmission medium. So peak amplitude of a signal is basically the absolute value of its highest intensity, which is proportional to the energy that it carries. So let me take a pen so that I can show you. So for any electrical signal, the peak amplitude is normally measured in volts. So here in this figure, the peak amplitude of two signals have been shown, whereas the peak amplitude of this first signal is higher than the peak amplitude of the second signal. Okay, so this represents the absolute value of the signal at its highest intensity represents the amplitude. So these all values, these all high intensity values which are absolute, particularly these values represents the peak amplitude of your signal. And if I compare these two signals, then I can easily observe that the peak amplitude of this first signal, I will represent it as 1 and 2. So first signal's peak amplitude is greater than the peak amplitude of the second signal. However, the phase and the frequency of both the signals are same, but their amplitude is different. Okay, so let's go to the next. That is the next parameter of representing a sine wave. So next parameter is frequency. We have seen amplitude. So a period which refers to the amount of time in second a signal needs to complete one cycle is called as period or one cycle. Okay, I will repeat it. The amount of time that signals takes in second to complete one cycle. So this is my one cycle, right? So we are representing this as one cycle. Okay, so whatever time that signal takes to complete this one cycle will be referred as a period. In contrast to this, the frequency is referred as the number of periods that signal completes in 1 second. Okay, so let's go back and we'll try to see the frequency and period. So as I mentioned, period is basically the amount of time in seconds a signal needs to complete the one cycle, and frequency refers to the number of periods that signal completed in 1 second. So note that here the period and frequency, they are just one characteristics defined in two ways. So we can say that the frequency is the inverse of period, or period is the inverse of frequency. And they can be mathematically represented as f is equal to 1 divided by t, which represents frequency is the inverse of period, and period is represented as inverse of frequency, that is t represents the period. So t, capital T, so capital T is equal to 1 upon f, that represents the period is the inverse of frequency. So now let us take some example to demonstrate the frequency and the period. Now this figure, it shows the two signal with the same amplitude and the phase, but they do have the different frequencies. So period is normally expressed in seconds, whereas the frequency is normally expressed in hertz, which is cycle per second. So the units of period and frequency we will see in the upcoming slide, but here we want to highlight something, that is, in this figure you can see that the first signal, it has the frequency 12 hertz. Why this frequency is 12 hertz? Because this signal, it completes 12 cycles in 1 second, and that's the reason the frequency of this signal in the first figure is 12 hertz. So as I just mentioned, the frequency is measured in hertz, it is expressed in hertz, whereas the period is expressed in second. Now the period or the cycle that this signal completed, the one cycle that this signal completed in a second, is basically a period. So here you can say that we know that the period and frequency, they are the inverse of each other. So if I want to find out the period, that is t, then I will simply calculate it as a 1 divided by 12 seconds. I know the frequency of this signal, the frequency of this signal is 12 hertz. So 1 divided by 12 is the period or the one cycle that signal completes in a second. Okay. So that seconds is, again, you know, we have to go backward and we have to recalculate it. Okay. Now as compared to this, the second signal, here you can say that the frequency of this second signal is 6 hertz. Why 6 hertz? Because the amount of cycles or the number of cycles that this signal completes in 1 second is 6. So 6 cycles the signal can travel in 1 second, and that's the reason the frequency of this signal is 6 hertz. And we know that how do we calculate the period? So period is, again, it is 1 divided by, or it is inverse of frequency. So 1 divided by 6 will be the period of this signal. Okay. So this signal takes 1 divided by 6 seconds to complete one cycle. On the counterpart, the first signal, it takes 1 divided by 12 seconds to complete one cycle, one period or one cycle. So there are different units of period and frequency. So let's go to it, as I mentioned already. So here, seconds, unit is seconds, that we can calculate the period. It may be millisecond, it may be microseconds, it may be nanoseconds, it may be picoseconds. So second is equivalently represented as 1 seconds, 2 seconds, 3 seconds, and 4 seconds. The value it takes. The millisecond unit, it takes the value, so 10 to the power minus 3 seconds. Microsecond will take 10 to the power 6 seconds. Nanosecond will take 10 to the power 9, and pico 10 to the power minus 12. Okay, so on. So the unit of frequency, so frequency, as we mentioned, it is expressed in hertz. So hertz, it takes the different value like 1 hertz, 2 hertz, 3 hertz, and so on. So kilohertz is the next unit of measuring the frequency. So 1000 hertz is equal to a 1 kilohertz. So it is 10 to the power 3 hertz is equivalent to a 1 kilohertz. So 10 to the power 3 hertz is basically equal to 1 kilohertz. Similarly, 10 to the power 6 hertz is equal to 1 megahertz. 10 to the power 9 hertz is equal to 1 gigahertz, and 10 to the power 12 hertz is equal to 1 terahertz. Okay, so alternatively I can say that the 1000 hertz is equal to 1 kilohertz, 1000 kilohertz is equal to 1 megahertz, 1000 megahertz is equal to 1 gigahertz, and the 1000 gigahertz is equal to 1 terahertz. So these are the different units to represent the period and frequency, or to measure the period and frequency. Well, now it's time for question. So you just note down the question. I'll just type the question in the chat box, and you're supposed to answer this question. So the power used at home, let's say, has a frequency of 60 hertz. Let me take some time. The power we use at home has a frequency of 60 hertz. Now we're supposed to calculate the period of sine wave which has the frequency 60 hertz. So calculate. I have posted the, so time is 12:40 now. So you're supposed to unmute your mic. Okay, no problem. So can you give the answer? Please calculate it. The power we use at home has the frequency of 60 hertz. Calculate the period of the sine wave. So how much time it takes to complete the one cycle if a frequency is 60 hertz? Yes, right. It will be 0.016 seconds. And if I want to convert it into the milliseconds, how many milliseconds it will be? Calculate the millisecond. Right answer. The answer is right. 0.06 seconds. Yes. So the right answer is, it is 16.6 milliseconds. So 0.016 into 10 to the power 3 will give me the millisecond answer. So that I have represented in the next slide. So this is the question that I have posted. The power we use at home has a frequency of 60 hertz. So the period of this sine wave can be determined as follow. That is T. We know that period is the inverse of frequency. So T is equal to 1 divided by F, 1 divided by 60, which gives me the answer 0.016 seconds. And when I want to convert it into the milliseconds, then I supposed to multiply this answer by 10 to the power 3, which gives me the millisecond. So 16.6 milliseconds, the time it takes to complete the one cycle. Similarly, I'll go to the next example. Express a period of 100 milliseconds in microseconds. The answer is given here in the slide itself. So we find the equivalent of 1 microsecond, and we know that is a millisecond. It's not micro, it's millisecond. So equivalent of millisecond is 10 to the power minus 3 seconds. And that's the reason we know that the 1 second, it is expressed as microseconds. In terms of mathematically, it is represented as, or its unit is 10 to the power 6. So now we'll make some substitutions for this. So here, let me take a pen so that I can explain you. So we have to express the 100 milliseconds in microseconds. Okay. So how do I convert the 100 milliseconds into seconds? So 100 milliseconds will be represented in seconds as 100 into 10 to the power minus 3. Remember, we are not converting from second to millisecond. We are converting from millisecond to second, and that's the reason we have taken minus here. So 100 into 10 to the power minus 3 seconds, which gives me the answer. So which gives me the conversion of millisecond to second. Then that is represented here. Now we have to convert this 100 milliseconds into microseconds. So 100 into 10 to the power minus 3 into 10 to the power 6. So I will just represent this term in a different way. I will represent this 100 as 10 square into 10 to the power 3 and then 10 to the power 6. So I will get the answer that if you take the when you evaluate this expression, you will get the answer 10 to the power 5 microseconds. How? 10 plus 6, 8, 8 minus 3. So 10 to the 8 minus 3 is 5. So 10 to the power 5 microsecond is the right answer. So either you can express it as the 100 milliseconds or 10 to the power minus 10 to the power 5 microseconds. Let's go to the next example. The period of signal is 100 milliseconds, and then what is its frequency in kilohertz? So first we change the 100 milliseconds to seconds, and then we calculate the frequency from the period. Okay, so that's given here. So how do we convert the 100 milliseconds into seconds? So we know that. So whenever we are performing reverse conversion, that is from milliseconds to second, we usually take 10 to the power 3. Milliseconds are always represented by 10 to the power 3, but when you are converting from second to millisecond. Now here we are converting from millisecond to second, so we are taking reverse of it. So that is 10 to the power minus 3. So 100 into 10 to the power minus 3, which gives me, so again what I will do, 10 to the power 2 into 10 to the power minus 3, which gives me the answer 10 to the power minus 1 seconds. Okay, so I got the period in terms of seconds. Now I will calculate its frequency. So frequency, we know that it is the inverse of period. So f is equal to 1 divided by t. We know what is t. T we have just calculated 10 to the power minus 1. So I'll just put this value here. So what I get, if I bring the denominator on the numerator, this 10 to the power minus 1 will get positive, and what we get is 10 hertz. Okay. Now when I want to convert this 10 hertz into kilohertz, then I simply have to take 10 into 10 to the power minus 3 kilohertz. Why? Because I am converting it from hertz to kilohertz. I know that 1000 hertz is equal to 1 kilohertz. Okay, and that's the reason because we are converting it to kilohertz so that we take 10 to the power 10 into 10 to the power minus 3 kilohertz. So that gives me the answer 10 to the power minus 2 kilohertz. So I hope you understood this units of measuring the frequency as well as the period of your signal. So let's go ahead. We have to see some fundamentals of frequency as well. So we already know that the frequency is the relationship of a signal to time, and that the frequency of wave is the number of cycles it completes it in a 1 second. But another way to look at frequency is the measurement of the rate of change. So we know that the electromagnetic signal are oscillating waveforms. That is, they fluctuate continuously above and below the mean energy level, right? So let's say that the frequency, it can be described in cycle per seconds, and we express it in hertz actually. In general, measurement of rate of change of signal with respect to time. So if the value of the signal over a very short span of time, then its frequency is very high. If the signal changes over a short span of time, then its frequency is very low. So we can say that frequency is one of the measure of whether your the rate of change of your signal with respect to time. So if there is changes in the signal within a short span of time, that means it has high frequency. If the signal changes with over a long span of time, if signal takes long time to get changed, that means its frequency is very lower. And we have seen that in this particular case where we have shown these two signal. Now the first signal, it has high frequency, whereas the second signal has the low frequency. Why? Because the first signal, it takes short span of time or a very little time to change the signal, whereas, and that's the reason it has a high frequency. Whereas in the second figure, the signal takes long time to get changed, and that's the reason it has a lower frequency. Okay, so if signal does not change at all, then its frequency is considered as 0, and in that case signal will be represented as just a straight line across your time and value axis. If signal changes instantaneously, then its frequency is infinite. That means within a fraction of second, within a picosecond, if signal gets changed, then we do consider that the frequency has the infinite number of value, and it is changing very instantly. Then comes to the next third parameter, that is phase. So phase describes the position of the waveform which is relative to the time 0. The term phase, it describes basically the position of the waveform relative to time 0. So if you think of the wave as something that can be shifted backward or forward along the time axis, then phase describes the amount of phase shift. Okay, if signal is fluctuating backward and forward, then for what purpose we are using the phase parameter in the sine wave? So phase parameter, it describes at how much amount of phase shift is there, how much amount of shift is there in the signal, and that we measure using phase. So it indicates the status of the first cycle. So phase is measured in degrees, or it may be measured in a radians. So phase generally, like, you know, the degrees like 360 degrees, 180 degrees, 90 degrees, and so on. So a phase shift of 360 degree, it corresponds to a shift of complete cycle. That means a complete period. Okay, so one cycle has the phase shift of 360 degrees, whereas a phase shift of 180 degree, it corresponds to a 1/2 of the cycle, that is half period, and a phase shift of 90 degree, it corresponds to the shift of 1/4 of cycle. Okay, and that represented here. So this shift has 360 degree phase shift. This signal has 360 degrees phase shift because the signal completes one cycle here. No, sorry. This is actually 180 degree. Let me take a eraser. Okay, so this first signal, I'll just mark it 1, 2, and 3. So this first signal, which is represented in this figure, it has a phase shift of 360 degree because one cycle is completed. Then this second signal, it has a phase shift of 90 degree because you can see that the signal starts here and it completes only 1/4 cycle here. Okay, that's it. So that's why it has a 90-degree phase shift. Whereas this signal, it has 180-degree phase shift because it completes the half cycle of the the entire wave. Okay, so that's why this signal has the 180-degree phase shift. So a sine wave with the phase of 0 degree, which starts at the time 0 with the 0 amplitude, and the amplitude is increasing actually substantially. In second figure, a sine wave with the phase of 90-degree, it starts at time 0 with the peak amplitude, whereas the amplitude of this signal is decreasing. In the third figure, a sine wave with the phase shift of 180-degree, it starts at time 0 with the 0 amplitude, and the amplitude is decreasing. Okay, whereas in this first figure the amplitude is increasing. So another way to look at this phase in terms of shift or offset, then we can say that a sine wave with the phase of 90-degree, with the phase of 0 degree is not shifted at all. A sine wave with the phase of 90-degree shifted to the left by 1/4 cycle. However, that signal does not really exist before the time 0. In third figure, in the third image, a sine wave with the phase of 180-degree, it is shifted to the left by half cycle. However, we can say that the signal does not really exist before the time 0. So this is one of the examples. So I'll just read this example so that you can solve it. Okay, so can anybody give me the answer of this? A sine wave which has an offset of 1/6 cycle with respect to time 0. What is its phase in degrees and radians? First you tell me in degrees. I will repeat the question. A sine wave has the offset 1/6, that is 1/6 cycles with respect to time 0. Calculate its phase in degrees. First calculate in degree and then calculate in radians. I have already mentioned that 360-degree is expressed as 2 radians, 2 nanoradians. So 1 radian is calculated as 360-degree divided by 2. That gives me 1 radian. So can anybody tell me the answer? Unmute your mic, or you can type your answer in the chat box. Yeah, so that's right answer. 60 is the right answer. Pi/6. Pi/6. It's not pi/6. It's pi/3. Okay. I think it's there. It's mentioned there. You can see the answers. Okay. Anyway. So we know that the cycle is given to us. The shift is the shift is given to us. The offset is given to us basically. That is 1/6. And we know that one complete cycle has the 360-degree. Therefore, 1/6 cycle will have the degree divided by 6 into 360. That gives me the 60-degree. So 1/6 cycle shift has the 60-degree angle. So what we are indicating with this, that means the signal is shifted with the 60-degree. Okay, so we are basically calculating, or we are finding the shift of signal. Okay, or the change of signal in terms of phase. Then we are supposed to calculate this degree into radians. So we got the answer 60-degree. So let us convert it into the radian. So I just mentioned the 360 radian, they have been 360-degree is equivalent to 2 divided by 360 radian. So 1 radian is calculated as 2 divided by 360-degree. So 2 pi divided by 360. Then this will get cancelled. We'll have the answer 2 pi by 6. So again 2 divided by 6, I will get pi by 3 radians, and then we convert it to 1.046 radians. So 1.046 is the right answer. I think time up, if I'm not wrong. Can anybody please tell me?
Yes, sir.
So if you are ready, I will take 2 minutes. Otherwise, I will stop. No problem. Otherwise, we will take wavelength and all this next concept, time and frequency domain representation of signal, and then bandwidth and the composite signal. These 4 topics will remain from this. So shall we take it in next lecture?
Sir.
Okay. So if you have any doubt in today's session, please tell me. Yes, tell me if you have any doubt. So we have seen what are the different forms of data, then what are the different forms of signal, then we have seen what is sine wave, what are the different parameters used to represent the sine wave, and we have completed all these 3 parameters which represents the sine wave. Okay. So there are 2 types of data, analog data and continuous data. Analog data takes the continuous values, and digital data, it takes the discrete values, right? The best example of analog data is the analog clock watch, and the example of digital data is the digital watch. Then we have seen the different types of signal, or signal take 2 different forms. One is the analog signal and other is the digital signal. So the signals, they can be periodic and they can be non-periodic, and we have seen that in data communication, a periodic analog signal and a non-periodic digital signals are preferred. The reason we have mentioned, because they consumes the less bandwidth on the transmission media, and that's the reason they are preferable. Then we have seen that the periodic analog signal, they have been further classified as simple periodic analog signal and composite periodic analog signal. A simple periodic analog signal cannot be further classified, or it cannot be further, we cannot create a multiple waves from the simple periodic analog wave. But in composite periodic analog wave, a multiple sine waves can be created from the original waves, right? And that's the reason it is called as the composite periodic analog wave. Then we have seen the sine wave. We know that sine wave is basically represented using 3 parameters that we have seen. It is namely amplitude, frequency, and phase. So frequency has one more characteristics, which is called as the period. So we have seen the relationship between period and frequency. So period and frequency, they are basically inverse of each other. Okay. So one period, the number of periods or the number of cycles that signal completes in 1 second represents the frequency of that signal, whereas the amount of time that signal takes in second to complete 1 period or to complete 1 cycle is called as period. 1 period or 1 cycle. Then we have seen the phase. So we have seen what are the different phase shifts. So basically phase, this parameter is used to observe the shift of the signal, okay, when it is moving back in the backward direction or in the forward direction, right? So that is what a phase. We have seen that phase is expressed in degrees and radians. So that's all from this lecture. In the next lecture, we'll see the remaining concepts. Thanks a lot. If you have any problem, please type in chat box. Otherwise, we will end this meeting. Is there any problem? Okay. Thanks a lot. So see you soon in the tomorrow's live session. You can end this meeting. Thank you for the patient listening.